Student, in previous class we discussed the term ligand, but what is ligand, what is its function, what are the reactions towards metal. Here the ligands are of different type. According to their density, ligands are divided into so many terms. One is monodendritic ligand, where the density means donation center is 1. That is like ammonia, NH3. Here the lone electron pair is nitrogen is 1, oxygen. Here also donation center is 1, F minus, Cl minus, NO2 plus, etc. Having the density, that is the reaction with the metal, the number of bond forms towards the metal is 1, so it is called monodendritic ligand. And also density, and also ligands are of different types, such as neutral ligand, such as the NH3, H2O, etc. are neutral ligand. There is no positive or negative charge. But in case of NO2 plus, NO plus, or NO2 plus, or NH2 plus, NH3, sorry, NH2, NH3 plus, etc., having one positively charged, so it is called the positively charged ligand. And also there are so many negatively charged ligand, that is F minus, Cl minus, OH minus, etc. are called negatively charged ligand. So one is monodendritic ligand, the other is bidendritic ligand. Bidendritic ligand means here the donation center is 2. Donation center 2 means like ethylene diamine or glycinate ion or oxalato. Ethylene diamine means EN, CH2, CH2, NH2, NH2. Here the donation center of donation center is 2, so it is called a didendritic ligand. That is called ethylene diamine. Ethylene means this part, and diamine means 2 number of nitrogen or ammonia present. So it is called ethylene diamine. And one is glycinato. Glycinato means GLY minus. Glycinato, formula of glycinato is CH2, NH2, COOH, that is called glycine, and the H plus, when removed, the negatively charged, is called glycinato. Here the donation center is 2. One is neutral nitrogen and the other is negatively charged oxygen, so it is called a didendritic or bidendritic ligand. Such as oxalato. Oxalato means OX minus 2. Here oxalato means COO minus, COO minus, oxalato. all are the example of bidendritic, or their density is 2. The other is tridendritic ligand. Tridendritic ligand means density is 3. Example of tridendritic ligand is diethylene triamine or diene. Diethylene means CH2, CH2, diethylene, CH2, CH2. Triamine means 1 nitrogen, NH2, NH2. Here the density is 3, that is number of donor center is 3. 3 nitrogen donate their electron pair to the central metal ion, so their density is 1 donor center, 2 donor center, and 3. So there it is called a tridendritic ligand. Similarly, a tetradendritic ligand is triene or triethylene tetraamine. Number of CH2 increases 1 unit and number of NH also increases 1 unit. So it is called triethylene, means 3 number of ethylene group, CH2 CH2 group 3, number of ethylene group is 3, and tetraamine means NH group is 4. Here NH group is 3, but in case of tetradendritic ligand, NH group is 4. Other is pentadendritic ligand. There is quite similarity between pentadendritic ligand and hexadendritic ligand. Best example of hexadendritic ligand is EDTA minus 4. Here full form of EDTA, ethylene diamine tetraacetic acid, but minus 4 present, so it is called ethylene diamine tetraacetate. That is, the structure is like that. Ethylene diamine means CH2, CH2, NH2, NH2. That is called ethylene diamine. Here tetraacetic acid or tetraacetate means the NH2, here the number of hydrogen is 2 and the number of hydrogen is 2. Total number of hydrogen is 4 and it is replaced by acetic acid group. Acetic acid group means CH3COOH group. Here nitrogen bonded to CH2COOH group and CH2COOH group. Here also CH2COOH and CH2COOH. It is called EDT, ethylene diamine tetraacetic acid. But if the H plus are removed, the 4 H plus removed, there is a charge of -4. EDTA, so we write EDTA -4. And the general structure of EDTA is, it is a structure of EDTA CH2, here the ethylene group, or diamine means 2 nitrogen donor center. Here also CH2COO minus, CH2COO minus, that part nitrogen having CH2CO minus is 2, and in that part nitrogen having CH2CO minus is 2. So all the in EDTA the CH2COO minus is 4, and the donation center is 2 nitrogen donor center is neutral and 4 oxygen donor center which is negatively charged. Total number of donor center to the metal atom is 6, 2 neutral donor center and 4 anionic donor center. But in case of it acts as a hexadentate ligand, but sometimes it acts as a pentadentate ligand. Here the pentadentate ligand, when EDTA acts as a pentadentate ligand, means pentadentate 1, 2, 3, 4, 5, like that, it is OH. Here H EDTA -3, it acts as pentadentate ligand. One CH3COO minus, so when the H plus is not removed, CH3COH part present, there is a minus charge, there is a minus charge, there is a minus charge. 3 donor center and 2 nitrogen donor center, that is 5. So total number of donor center is 2 neutral donor and 3 negatively charged oxygen donor. So total number of donor center is 5. It acts as a pentadentate ligand. This EDTA, when the donor center of EDTA is 4, it acts as an tetradentate ligand, it acts as an tridentate ligand. So there is another term when the denticity of EDTA varies, it is called a flexidentate ligand. Flexidentate ligand means when EDTA having this formula EDTA -4, it acts as an hexadentate ligand, and when H EDTA -3, it acts as an pentadentate ligand. Whether it is acts as an tetradentate ligand, tridentate ligand, according to their denticity or donation capacity to the central metal ion, so it acts as a flexidentate ligand. And there is another term, ambidentate ligand. Ambidentate ligand means, example of ambidentate ligand is CN minus. CN minus means donation center, when the metal atom attached to the CN, that is CN, C donation center attached to the metal ion, and it is probably that the nitrogen donor center when attached to the metal ion. So there is a probability of CN minus or cyanido ion to act as an C donor center or N donor center. So it is called ambidentate ligand. There is also a classical ligand or non-classical ligand. Classical ligand means we write that F minus, Cl minus, H2O, NH3, etc. are called classical ligand. That is, classical ligand generally forms a ligand to metal a sigma bond. Those ligand which forms generally a sigma bond, that is donation of lone electron pair to the metal ion from ligand, is called classical ligand. There is also a term non-classical ligand. It may be pi acidic ligand, or sigma donor pi acceptor ligand. Classical non-classical ligands are generally found in gaseous salt. The example of non-classical ligand is CH2 double bond CH2, that is ethylene, benzene, etc. are called non-classical ligand. Example of non-classical ligand is gaseous salt, pretty, Cl, 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 double bond CH2, CH2. It is an example of non-classical ligand where platinum bonded to a double bonded hydrocarbon, that is a double bonded hydrocarbon, that is platinum attached to the double bonded CH2 double bond CH2. It is called a non-classical ligand. There is also an example of non-classical ligand is ferrocene, Fe. Here Fe, ferrocene, it is called a non-classical ligand, and benzene ring also acts as a non-classical ligand. There is a ligand, pi acid ligand, that is pi bond formed. It is called pi acid ligand. The ligands which acts as a sigma donor and pi acceptor, it is very important, that is CO. Example of sigma donor and pi acceptor is CO, carbon monoxide. Carbon monoxide, there is also an effect called synergic effect. Synergic effect means when the neutral ligand CO or carbon monoxide bonded to a metal atom, the metal atom, when bonded to a metal atom, that is like that, C, like that. Here the carbonyl compound CO acts as a ligand, and firstly it donates its lone electron pair to the metal atom and forms a sigma bond. So it is called sigma donor. Sigma donors mean by the donation of lone electron pair to the metal atom, it forms a sigma bond. And reversely, the metal atom gives the pi star antibonding orbital, gives lone electron pair of to carbonyl carbon atom to its pi star antibonding orbital. So there is a bond formed is called pi bond. This pi bond forms by the acceptance of the lone electron pair from the metal atom to the carbonyl carbon atom. So it is called pi acceptor. This type of ligand shows a effect. This effect is called synergic effect, in which sigma donor as well as pi acceptor type of ligand present. There is also a ligand called homoleptic and heteroleptic ligand. Homoleptic ligand means such as CO, NH3 or 6, Cl3. Here the number of coordination number or the ligand attached to the central metal ion is 6, and all the 6 are ammonia molecule. So similar type of ligands when used, it is called homoleptic. And if there is two or more different type of ligand used, it is called heteroleptic, such as CO, NH3 whole 4, Cl2, Cl. It is called a heteroleptic complex. So homoleptic and heteroleptic. Hetero means different type of ligand attached to the central metal ion. There is another type of ligand that is called macrocyclic ligand. Macrocyclic ligand is the ligand which are generally example of macrocyclic ligands are crown ether, such as crown ether, such as like that. The central metal ion bonded by this oxygen atom, and it is a crown ether type ligand. It acts as a crown ether ligand. It is called 1 2 3 4 5 6 7 8 9 10 11 12 12 crown 4. It is called 12 crown 4. Similarly, there are many types of crown ether, 16 crown 4, and like the structure is 16 crown 4 structure is that is 16 crown 4. Total number of the nomenclature for that crown ether is 12. Here 12 is 1 to total number of including oxygen atom, and the carbon atom total number is 12 and oxygen atom present is 4. It is called 12 crown 4 and it is 16 crown 4. These are the different type of ligands present, or different type of according to their density, whether it is mono, bi, tri, etc., or neutral or negatively charged or positively charged. There is an pi sigma donor, pi acceptor, pi acidic ligand, etc. There is another type of ligand which is called bridging ligand. Bridging ligand means, example of bridging ligand is Cn minus O minus 2, NH2, etc., called NH2 minus, etc., called bridging ligand, such as example of bridging ligand is Cn. When Cn, C111N, metal atom, there is another metal atom. So it acts as a bridging ligand, means these two type of metal atom bridged by a ligand Cn. So it is called a bridging ligand. There are different type of example, O minus 2, NH2 minus, etc. There is another type of ligand which is called chelating ligand. It is quite most important ligand explained in this chapter. Chelating ligand. Why chelating complex is more stable? It is also explained here. Chelating ligand, example of chelating ligand example is EN or ethylene diamine or glycinate minus, etc. Example, simple example of chelating ligand. And the complex formed by this ligand is called chelating complex or chelate complex. Chelate complex generally are highly stable, as there are 5 or 6 member ring present, so they are highly stable. So the chelating complex, stability of chelating complex or chelating ligands are more stable complex form. That is the that is explained by the reaction of this chelation reaction is highly favorable or spontaneous. It is explained by this simple reaction when CO NH3 whole 6 Cl3 with EN, 3 molecule of EN, and forms CO EN whole 3 plus 6 NH3. Here at the left hand, total number of molecule is 3 EN and 1 this compound. So total number of molecule is 4. Here total number of molecule is 6 ammonia and 1 this molecule. So total is equal to 7. Here we know that according to Gibbs free energy, delta G is equal to delta H minus T delta S. Delta is called entropy or randomness, or the number of molecule where increases, that is called entropy also increases. Here the delta S is 7 minus 4. Delta S means here the entropy arises due to the increase in number of ion, number of atom. Here number of atom is 7, here number of total atom is 4. So delta S is equal to 7 minus 4 is equal to 3, that is positive. As the value of delta S is positive and very high, so delta G is also be negative, and the negative value will be very high. That is the delta G is highly negative. According to this Gibbs free energy equation, if delta G is negative, then the reaction will be spontaneous. So it can be explained that here the delta S is positive, and as a result delta G is negative, so the reaction will be spontaneous. It is called a chelate complex. Chelate complex. When CO reacts with EN, that is formed a chelating complex CO EN whole 3, like that. CO, here EN, here EN, here EN, like that. It is called CO EN whole 3 plus 3 complex, and it is highly stable. That is called a chelating complex. There are such as plus 3. So the example of chelation, or the reaction of chelation or chelating complex or chelating ligand is here. There is also a ligand present, labile complex formed. Labile complex is the complex where the number of ligand or the ligand easily replaced by another type of ligand, and the first complex is called labile complex. Labile example of labile complex is CuH2O whole 4 plus 2 when reacts with 4 ammonia forms CuNH3 whole 4 plus 2 plus 4 H2O. Here the copper when bonded to H2O ligand, this H2O ligand replaced by 4 NH3, and this complex is called labile complex. Labile complex is that complex where the ligand is replaced by another type of ligand and form a complex. It is a deep blue in color, but it is just blue in color. This complex is called labile complex. In that today's class we discussed the type of ligand. Here we also discussed about the effective atomic number. Effective atomic number means scientist Sidgwick first show that the coordination number 4 or coordination number 6 complexes are highly stable. Coordination number 4 and coordination number 6 complexes are highly stable, and this type of stability can be explained by Sidgwick by effective atomic number. Effective atomic number means the total atomic number or total number of electrons surrounded by a central metal ion is nearest to the noble gas, such as scientist Sidgwick effective atomic number. Give a simple example of effective atomic number. Calculation of effective atomic number is CO NH3 whole 6 plus 3. Here we find out the effective atomic number of the central metal ion. The central metal formula of the effective atomic number is equal to the central metal ion's atomic number, that is atomic number of cobalt, atomic number of electron, that is cobalt CO, and its oxidation state minus its oxidation state plus 2 into number of coordination number or number of ligand. 2 into coordination number. It is the formula of effective atomic number. Here how to calculate the effective atomic number is here, and the calculation of effective atomic number of CONH3 whole 6 plus 3 is given below. CO is 27 minus oxidation state is plus 3 plus number of ligand attached or coordination number is 6, so 2 into 6, total 24 plus 12 is equal to 36. Here we can also explain the coordination number, the effective atomic number of CONH3 whole 5 Cl plus 2. Here the coordination number of here the central metal ion is CO or cobalt, that is 27 minus its number of oxidation state is 3 plus here the total ligand is 5 and 1 Cl, that is 6. 6 into 2 or 2 into 6 also be 36.